Okay, in this video, I'm going to continue going through AQA AS paper 1 chemistry. So this is the June 2018 paper. Starting off at question 8, I did questions 1 to 7 in an earlier video. Okay, so first question is about the time of flight mass spectrometer and two isotopes of bromine, 79 and 81. Okay, so electron impact ionization, and they're accelerated to the same kinetic energy, as of course always happens in one of these spectrometers, and travel through a flight tube that was 0.95 meters long. Okay, it gives us the time taken for the 79 bromine atoms. Now, first question is calculate in kilograms the mass of one ion of 79 Br plus. So we're going to say 1 mole of those ions, 1 mole of 79 Br, that's going to have a mass of 79 grams. We need to convert that into kilograms, so that divided by 1,000 is equal to 0.079 kilograms. That's the mass of 1 mole, so for 1 ion, we need to divide by the Avogadro constant, so it's 0.079. You get 6 times 10 to the 6.02, sorry. Use the Avogadro constant here. 6.02 times 10 to the 23 ions in 1 mole. So divide the mass of 1 mole by the Avogadro number, and that will give us 1.311 times 10 to the minus 25 kilograms. Okay, that's the first part of that calculation done. Now, the next part, we need to calculate the time taken for the 81 bromine ion to travel. They give us the time for the 79. Okay, we have to work it out for the 81. Now, they give us a bit of information here that's actually not strictly necessary, and they give us the length of the flight tube. And the long way around of doing this is you can work out the velocity of the 79 using the distance divided by the time given. They'll give you that. From the velocity, we can then work out the kinetic energy of the 79. We know that the kinetic energy of the 79 is the same as the 81. And then we put all those numbers in. We know distance, we know mass, we know the velocity, and we can just work out, we know the kinetic energy, and we can work out the time taken. That's quite a long way of doing it. There's a quicker way of doing it, and you don't need the distance. So what I'm going to do here is show you how the quick way of doing that. Right, so I'll just get rid of this here. The kinetic energy of the 79 is equal to half mv squared. And we know that v is equal to distance over time, so I'm going to say so the kinetic energy is also equal to a half m d squared over t squared, and that's the time taken for the 79. Right, the mass of the 79 we worked out before is the it's going to be the mass of 1 mole, 79, so kinetic energy is equal to a half. The mass of 1 mole is 79 divided by 1,000, so it's in kilograms, and divided by the Avogadro constant L. So we replaced m with that little bit there, times d squared over t squared 79. Now we know the kinetic energy, this is the kinetic energy for the 79, is equal to the kinetic energy for the 81. And the kinetic energy for the 81, I'll put here, is the same as that, is going to be a half times the mass of 1 mole, which is 81, multiplied by d squared over 1,000 L, and the time taken for the 81. Now we can cancel out most of that stuff, so we're going to get rid of the half, the 1000, because the kinetic energies are the same. Avogadro constant, and the d squared. That's why we don't need the length of the tube. So we end up there with 79, which is the AR of the atomic mass of that isotope, over the time squared for the 79 isotope is equal to 81, the time squared for the 81 isotope. We need to find out the time squared for the 81 isotope, so let's rearrange that. So that's going to be equal to 81 over 79 multiplied by the time taken for the 79. Let's put the numbers in there. So 81 over 79 multiplied by the time for the 79 ion is that 6.69 times 10 to the minus 4, and we've got to square that. Okay, so we then get the time for the 81. Put those numbers into the calculator, and we get for that 4.588 times 10 to the minus 7. Square root that to get the time for the 81. That is equal to 6.77 times 10 to the minus 4 seconds. Okay, quick common sense check. It's ever so slightly longer, isn't it, than the time for the 79, which is up there, which is right, because the 79 is a bit lighter. So with the same kinetic energy, it's going to be moving a bit faster. Okay, so that is the way I'll do that one. Okay. Right, fairly standard question. How ions are detected and they're detected and the relative abundance is measured. So the detector, well, electrons leave the detector and they neutralize the positive ions. So the flow of electrons is a current, and the size of the current is proportional to the abundance of that ion. So that's your 2 marks there, 1 for each line, really. Okay, so fluorine compounds. Draw the shape of a krypton difluoride molecule. So what we've got to do here is I always cross it out because it's not the answer, but draw a little dot cross diagram. So here's my krypton. There's fluorine. Right, you're going to have a dot and a cross where each bond is. The fluorine has got 7 electrons, to draw 7 more. Same for the fluorine on the other side. Don't worry too much about that. Now krypton has going to have 8 of its own electrons. It's in the noble gas. Okay, it's going to 8 of its own. I have so far drawn just 2 crosses. Okay, there in kryptons. So I need to draw 6 more crosses. Okay, so I'm going to have 1 lone pair, 2 lone pairs, 3 lone pairs. Okay, so what you have got there is you've got 5 bonding pairs. Sorry, 5 pairs, 2 bonding, and 3 lone pairs. Now remember, when you have 5 pairs, you always have this sort of shape where you have bipyramidal. You have 3 pairs in the same plane, like trigonal plane, that sort of thing, and then you have 1 pair sticking up and 1 pair sticking down. So you've got 3 lone pairs in this sort of plane bit there, and you've got the bonding pairs going to fluorine sticking up, sticking down. The bond angle there is going to be 180 degrees, and you would call that a linear molecule, right? Which you could probably just guess, saying that, you just said there's 2 bonding pairs, you get the right answer, but you wouldn't get the marks. You've got to put in those lone pairs and be aware that there are 3 lone pairs there. Right, Now, without drawing a dot cross diagram here, because they tell us, they say for in an OF2, you have got 2 bonding pairs and you have got 2 lone pairs. Okay. Explain how the lone pairs influence the bond angle. Right. Normally with 4 pairs, you get a tetrahedral arrangement, don't you? And when you have a tetrahedral, for example, in methane, you would expect a bond angle of 109.5. But the bond angle here is smaller. It's like water, that's going to be about 104.5. And you need to say 2 things. First of all, the repulsion between the lone pairs and the lone pair is strongest of all, because the shape of the lone pairs are more bulbous. So that lone pair repulsion is greater than lone pair bond pair, so the repulsion there, which is greater in itself than the bond pair repulsion. And that all has the effect of reducing the bond angle from 109.5 down to about 104.5. It's the same bond angle as in water. Okay. Sorry, that's copied in twice. Ignore that. 9.2. Okay. So question 10 here. Right, which row shows the bonding in ammonium chloride? Okay. So wait, 9.3, sorry about that. There is a question missing there. 9.3, it asks us about the the strongest kind of intermolecular force you get present in the so I'll paste that in 1 minute. A 3-mark question. Right, here we go. Right, the silicon tetrafluoride is a tetrahedral molecule. Deduce the type of intermolecular forces and explain how this kind of intermolecular forces arise and why no other type exists in SiF4. Okay, so silicon SiF4 is like this. It's tetrahedral. It's showing it in 3 dimensions, and that's really important because it's symmetrical. So although those fluorines are very electronegative, and each one will be delta negative, and the silicon will be delta positive, there's no dipole on that molecule. The center of positive charge and the center of negative charge are both in the very middle of the molecule there. There's no dipole, so you can't get dipole-dipole interactions. So the strongest kind of intermolecular forces you can get, then the only intermolecular forces you can get are van der Waals. Now for 3 marks, you've got to explain how this kind of intermolecular forces arises. So you would say you have a temporary, or sometimes called an instantaneous dipole on the molecule due to fluctuations and the negative charge cloud, so random fluctuations. And then you need to say that those temporary dipoles, they induce dipoles in neighboring molecules. And the van der Waals force is the attraction between one induced dipole and the temporary dipole on the next molecule. And that's easily enough for 3 marks there, I think. Right, on to the multiple choice section of this paper then. Which row shows the bonding in ammonium chloride? Now, ammonium chloride, you have got an NH4 plus ion and a Cl minus ion, so it's ionic, definitely. But also in the ammonium ion, well, you've got 3 bonds in ammonia, And then in ammonium ion, that forms a dated bond to an H plus ion. So you've got dated bonds. So you've got all three there. So it's this one, C. You've got covalent, dative, and ionic bonds. How many protons are there in 6 grams of nitrogen gas? So let's do moles, N2. Of N2, that's important, N2, not N, is mass over AR, over MR, sorry. So that's going to be 6 over 2 times 14 for nitrogen is 28. That's equal to 0.214 moles, okay, of N2. Now, how many protons in 1 and 2? Right, you've got 2 nitrogen atoms, each have got 7 in there, so it's equal to 14. So the number of protons is, we're going to multiply this by the number of moles, so 14 times 0.214, and then multiply that by the Avogadro constant. That gives us 1.8 times 10 to the 24, that one there. Okay, so work out the number of moles of N2. Then if you like, work out the number of molecules of N2. And then you've got to remember there are 14 protons in each molecule, so multiply the whole thing by 14. Right, periodicity. This shows the property of period 3. Which property does that show? Well, it doesn't show ionic radius. Of course, the ionic radius, that would decrease, always decrease as you go across the period as you get more nuclear charge, but the same quantum shell being filled, so that's not right. Electronegativity, well, that increases as you go across because you've got more protons in the nucleus. Okay, so not that. First ionization energy, that's that has wobbles in it, but it's a general upward trend, isn't it? It is melting point, is D. And of course, silicon is very high because it's giant covalent. These are all simple covalent, but you've got P4, which is a smaller molecule than S8, so it goes up again and then down again because it's Cl2, and finally down for Ar. And then you've got aluminium, magnesium, sodium there, or metallic lattices. So a bit going on a bit there, but it's just basically melting point, isn't it? Right, now this is a gas volume calculation. We've got to remember that the number of moles, the volume of a gas, is proportional to the number of moles. So for example, in this question, if you had 30 centimeters cubed of nitrogen, that would contain the same number of moles as 30 centimeters cubed of fluorine, or 30 centimeters cubed of NF3, or you could have 15, it's the same. Yeah, okay. So the volume is proportional to the number of moles. I don't like having fractions in that because it puts me off, so I'm going to change it to N2 3F2 goes to 2 NF3. Okay, so it says we start off with 30 centimeters cubed of nitrogen. Now that can react with 1 mole of nitrogen reacts with 3 of fluorine, so that could react with 90, but we haven't got 90, we've only got 60. Okay, so let's write down there. If we've got 60 of fluorine, how much? It's only a third, so that can only react with 20 of the N2. So that means we're going to have 10 centimeters cubed of it left over at the end. Right, 60 centimeters cubed of F2, so there's a 3:2 ratio, so that's going to give us 40 centimeters cubed of NF3. So the total volume is 40 plus 10 at the end, which is 50. Right, straightforward knowledge recall one now. Which substance is used to reduce titanium 4 chloride in extraction of aluminium? It's magnesium. Okay, it's going to be quite a reactive metal. That's in the group 2 section of the spec. Sort of a one line bit of knowledge. Which statement about barium sulfate is correct? Now, barium sulfate is very, very insoluble. Okay, so it's not soluble in water, is it? That's the whole thing about barium sulfate, is insoluble. It's used in medicine because it doesn't dissolve. That's right, because it's toxic. Barium ions are toxic, but it doesn't matter because it won't dissolve. It's not yellow. Most group 2 solids are white, and it won't react with barium chloride. So B is the right one. You should just know that it's very insoluble. Which statement about the reaction between concentrated sulfuric acid and solid sodium bromide? Well, concentrated sulfuric acid will oxidize bromide ions to Br2, and in the process, the sulfuric acid gets reduced from the +6 oxidation state down to the SO2. Right, so bromide ions are reduced, wrong because they're oxidized. Hydrogen, bromide, and sulfur, that's not right. Iodine can reduce it, even if that's +4. Iodine can reduce it to sulfur, which is 0, and H2S, which is -2. But bromine isn't a strong enough reducing agent to do that. Sulfuric does act as an oxidizing agent. And bromine is formed, but you don't get hydrogen sulfide. Okay. So C is right there. 17. Which compound is used to treat symptoms of indigestion? Right, it's got to be able to react with an acid, but it mustn't be soluble to make an alkaline solution, which is corrosive. So magnesium hydroxide is very insoluble, so that would be suitable. This one wouldn't be insoluble because that would make that's about pH 12, and that's very corrosive. Calcium oxide, that would also react to make calcium hydroxide. That would be very alkaline and corrosive. So magnesium hydroxide is the answer. And they use that instead of magnesium oxide would react with acid, but I think magnesium hydroxide reacts more readily. Okay, which element has the highest first ionization? We've got aluminium, phosphorus, silicon, and sulfur. So we've got this lot here. Okay, so let's write down. This is the P block. So when you do the first ionization energy, aluminium, you're removing it from 3. You're moving it from 3p every time. Right. So because the nuclear charge is increasing, it should go up. But if you remember with sulfur, because that's 3p4 and you've got an electron, you get pair repulsion there because you're removing it from there. You remember that? It's going to go down a bit for sulfur. So the highest one would be phosphorus, B. A solution of 500 centimeters contains 150 grams of ammonia. The concentration in mole per decimeter cubed of ammonia. So what we've got to do there, moles of ammonia is equal to mass over mR. 150 over NH3, so that's an mR of 17. So that's going to give us 8.82 moles. Now we have to do concentration is equal to moles over volume in dm cubed. So that's 8.82 divided by the volume, which is 500, so that's 0.5 dm cubed, which gives us 17.6. So it's that one there. Very concentrated solution. Conc ammonia. Ammonia is very soluble in water, can form hydrogen bonds with water. So that's why. Right, now this is about titration. There's a few questions here, 20 to 24 on a titration technique, okay? So there's going to be some mistakes in this. A student devised an experiment to find the concentration of sulfuric acid in a sample of battery acid. So use a measuring cylinder to transfer 10 centimeters cubed of battery acid. That's a mistake. Should use a pipette really there, shouldn't they? Distilled water I'd added to the volumetric until it reached 250. Now, if you read later on, I think you need to invert, and that's quite a mistake he's made here. It doesn't say he's done that, and that will mean when if you do that, and you make up your solution, you're going to start off, there's your battery acid like there, and then you're going to add the last bit of distilled water, and so that first bit, they won't mix very well, and that first pipette full you get out is going to be mostly distilled water, and so it's not going to work. All right. 25 sample was added with dilute acid was transferred to the volumetric using a pipette. That's good practice. That's fine. He used methyl orange indicator, a few drops. Methyl orange is fine for this titration, and that's okay. No problem there. And the titration was repeated 5 times. Okay, but that's okay. But he didn't get concordant results. Okay, methyl orange, it tells us, is red in acid and yellow in alkali. So when it's neutral, you should realize that it's kind of an orangey color at the end point. A mixture of the acid, a mixture of the red and the yellow. Which suggestion would improve the chances of obtaining concordant titers? Invert the volumetric flask. That's the one, because he's the first lot of stuff he gets out here is mostly water, and the next one's going to be really concentrated. That's why it's different every time. Wash the pipette with distilled water. That's going to mess things up because you don't want to do that. You're diluting this. You want you're going to be diluting the acid with water in the pipette. You should rinse it with the acid, if anything. Adding more indicators is not good. You should always just add a few drops. If you use a more concentrated solution of sodium hydroxide, that wouldn't really help, because that means you would use less of it every time, which would make your percentage error bigger. Okay, so I think A is the best answer there. Which suggestion about rinsing the conical flask would improve the accuracy? Rinsing with acid wouldn't be good, because you want to add exactly 25 centimeters cubed of acid. You rinse it with acid, you have a little bit more. Rinse with alkali, that would be no good. It obviously neutralize some of the acid. Rinsing with water is fine, because it doesn't matter if you leave a little bit of water left in there, because you've got a wet conical flask. That's fine, because you put in there with the pipette exactly 25 centimeters cubed of acid, so you know the number of moles of acid you're adding every time. So C is the best one. Not rinsing wouldn't be good, because you'd have some acid or alkali left over in the conical flask from the last experiment. Which suggestion would reduce the overall measurement uncertainty? Use less concentrated alkali in the burette. That would, less concentrated, you'd have a greater volume for your titers, and percentage error or uncertainty is equal to the accuracy of the burette, which is usually 0.15, over the titer times 100. So the bigger the titer, the smaller the percentage error. So you want to use less. That's good. Let's just check the other ones. There'd be no advantage in using phenolphthalein over methyl orange here. They're both fine. Use smaller samples of the diluted acid. That wouldn't be good, because then you'd use smaller volumes of NaOH. The titer would be smaller, so you get a bigger percentage error. And starting at the 0 mark doesn't make any difference at all. There's not any point in doing that. Which of these is important in ensuring the student's experiment is safe? Do it in a fume cupboard. There's no need to do that. There's no gases produced in the reaction. Wear gloves when measuring out battery acid. That might be a good idea, because the battery acid could be concentrated. Wash hands before doing the titration. Well, that will help your accuracy and stuff, but not safety, really. Okay, it's not going to affect safety. That's not really a great one. So B is the best one to choose there. And 24, the final question on the paper. Right, so what's the color change? So it told us that methyl orange, earlier in the question, is red in acid, and it is yellow in alkali. And what are you doing? You're adding you've got acid in there, so it's going to be red to start off with. As you add your alkali, if it goes yellow, you've gone too far. You've made it alkaline. You wanted to get it just before it goes alkaline, so you want it to be orange. So it's going to be red to orange. B is the right one. Okay, that is the end of that paper.